Chapter 8, Work and Energy. This lecture will help you understand kinetic energy and the work-energy theorem. Kinetic energy is the energy of motion. All moving objects have kinetic energy. The more massive an object or the faster it moves, the larger its kinetic energy. Kinetic energy is a property of an object and not a property of position. Kinetic energy is always positive, never negative. Kinetic energy is defined as the energy of a moving body. The equation for kinetic energy is 1/2 the mass times the speed squared. When work is done on an object to change its kinetic energy, the amount of work done is equal to its change in kinetic energy. The equation of the work-energy theorem is the net work done is the change in kinetic energy. Work is force times distance, and the change in kinetic energy is the change in 1/2 times the mass times the speed squared. If there is no change in object's energy, then no work is done on the objects. This applies to potential energy. For a barbell held stationary, no further work is done, therefore no further change in energy. It also applies to decrease in energy. The more kinetic energy something has, therefore the more work is required to slow it or stop it. The work-energy theorem is the idea that energy and work can be directly exchanged for one another. For example, if you do 3 joules of work to get a bowling ball moving, it now is moving with 3 joules of kinetic energy. The work-energy theorem applies to decreasing an object's speed, such as reducing the speed of an object or bringing it to a halt. When the brakes are applied to slow a moving car, work is done on it by the friction force supplied by the brakes times the distance over which the brakes are applied. A pile driver with mass 10,000 kilograms strikes a pile with velocity 10 meters per second. A, what is the kinetic energy of the driver as it strikes the ground? B, if the pile is driven 20 centimeters into the ground, what force is applied to the pile by the driver as it strikes the pile? We know the mass and speed, which allows us to calculate the kinetic energy before the interaction, 500 kilojoule. The kinetic energy after the interaction is 0. The driver has stopped. The change in kinetic energy is minus 500 kilojoule. The minus sign indicates the driver is doing work on something. The work done is the change in kinetic energy. Since work is force times distance, we can find the force required, which is 2.5 times 10 to the 6th Newton. Notice that we have dropped the minus sign. This is because the work is being done on the pile and must be positive. A 60-gram bullet is fired from a gun with 3,150 joules of kinetic energy. Find its velocity. The kinetic energy is 3,150 joules. The mass is 0.06 kilograms. The definition of kinetic energy is 1/2 the mass times the speed squared. The velocity can be found as the square root of twice the kinetic energy divided by the mass, or 324 meters per second, to 3 significant figures. Thermal energy is the sum of the microscopic kinetic and potential energies of all the atoms and bonds that make up the object. An object has more thermal energy when hot than when cold. The basic energy model is that within a system, energy can be transformed from one type to another. The total energy of the system is not changed by these transformations. This is the law of the conservation of energy. Energy can also be transferred from one system to another. The mechanical transfer of energy to a system via forces is called work. In the box, the system kinetic energy can be exchanged with potential energy, and both can be converted to thermal energy. But notice that thermal energy is never converted back to kinetic energy or potential energy. It is a one-way process, and we call that a conversion to waste heat. The system can also absorb energy from the outside on the left, and it can emit energy to the outside on the right. In the basic energy model, the energy of the system E sub cis is equal to the kinetic energy plus the potential energy plus the thermal energy. Must a car with momentum have kinetic energy? A, yes, due to motion alone. Yes, when motion is non-accelerated. Yes, because the speed is a scalar and velocity is a vector quantity. D, no. Answer is A, yes, due to motion alone. Acceleration, speed being a scalar, and velocity being a vector quantity are irrelevant. Any moving object has both momentum and kinetic energy. Consider a problem that asks for the distance a fast-moving crate slides across the factory floor and coming to a stop. The most useful equation for solving this problem is A, F equal ma, B, F times delta T is delta mv, C, K is 1/2 mv squared, or D, F delta S is delta 1/2 mv squared. The answer is D. The work energy theorem is the physicist's favorite starting point for solving many motion-related problems. Energy transformed without net loss or net gain in the operation of a pile driver. When raised, the driver has potential energy. When released, that potential energy is converted to motion or kinetic energy. The law of conservation of energy states that the total energy of an isolated system remains constant. It is said to be conserved over time. Energy can neither be created nor destroyed. Rather, it transforms from one form to another. For instance, chemical energy can be converted to kinetic energy in the explosion of a stick of dynamite. The work done in braking a moving car to a stop is the force of tire friction times the stopping distance. If the initial speed of the car is doubled, the stopping distance is A, actually less, B, about the same, C, twice, D, none of the above. The answer is D, none of the above. Twice the speed means 4 times the kinetic energy and 4 times the stopping distance. If we compare kinetic energy and momentum, we note that both depend upon mass and velocity. Momentum depends upon mass and velocity, while kinetic energy depends upon mass and the square of the velocity, or the speed. Momentum is a vector quantity, but kinetic energy is a scalar quantity. In everyday usage, conservation is defined as to save. In physics, conservation means to remain unchanged. The law of conservation of energy states, in the absence of external work, input or output, the energy of a system remains unchanged. In other words, energy cannot be created or destroyed. In the basic energy model, when a system is isolated, E sub cis, the total energy of the system is constant. In other words, the change in the system energy is 0. For a system with both internal interaction forces and external forces, E sub cis, the total energy of the system, changes only if external forces transfer energy into or out of the system. If work is done on the system, it is positive. It is energy into the system. If work is done by the system, it is negative. It is energy out of the system. The change in the energy of the system is equal to the external work done on the system. The change in the energy of the system is also defined as the energy of the system after the interaction minus the energy of the system before the interaction. You think we could write the energy before as the kinetic energy plus the potential energy plus the thermal energy before the interaction, and the energy of the system after the interaction as the kinetic energy plus the potential energy plus the thermal energy after. But we do not. The energy of the system before is the sum of the kinetic and potential energy. The energy of the system after is the kinetic plus the potential plus the change in thermal energy. Thermal energy is an end product. Energy is dumped to thermal energy and is never recovered. It appears only after an interaction. Consider the system of a bow and arrow. In drawing the bow, we do work on the system and give it potential energy. When the bowstring is released, most of the potential energy is transferred to the arrow as kinetic energy, and some to heat the bow. Suppose the potential energy of a drawn bow is 50 joules, and the kinetic energy of the shot arrow is 40 joules. Then, A, energy is not conserved, B, 10 joules go to warming the bow, C, 10 joules go to warming the target, D, 10 joules is mysteriously missing. B, 10 joules go to warming the bow. The total energy of the drawn bow, which includes the poised arrow, is 50 joules. The arrow gets 40 joules, and the remaining 10 joules warms the bow, still in the initial system. For an isolated system with no losses to thermal energy, the change in potential energy must equal the change in kinetic energy. The diagram shows the position of a pendulum. At the left is the beginning of the swing, and the kinetic energy is 0. All the energy is potential. As the pendulum swings, the speed increases, and so does the kinetic energy. The potential energy has decreased. At the lowest part of the swing, on the left, the potential energy is 0, and the kinetic energy is maximum. The pendulum continues to rise and reaches the extreme, where the kinetic energy is again 0, and the potential energy is again at a maximum. The height of the pendulum, in the absence of friction, is the same as the start and the end of the swing. A pile driver falls freely from a height of 3.5 meters above the pile. What is the velocity as it hits the pile? First, we find the initial and final potential energy of the driver. We set the final position as 0 meters. Notice we do not know the mass of the pile driver in this problem, but we do know the initial height above ground. Next, we find the change in kinetic energy. We do not know the mass or the final speed, which we call V. The initial kinetic energy is 0. The final kinetic energy is 1/2 the mass times the speed squared. For our final step, equate the change in potential with the change in kinetic energies. We have relations for these that both involve the mass. See how the mass cancels. This allows us to find the final speed as 8.28 meters per second. Work is done to take the roller coaster car from the beginning of the ride to the top of the structure to give it potential energy. After it leaves the peak of the ride, the sum of its potential energy and its kinetic energy is equal at each point on the ride. Watch the roller coaster video on Blackboard. This slide lists a summary of formula in this chapter. Find the kinetic energy of an 86 kilogram scooter moving at 2.2 meters per second. 1 joule is equivalent to 1 Newton meter, which is equivalent to 1 kilogram meter squared per second squared. Pause the video to work on the problem. Did you get 210 joule? Calculate the number of joules of potential energy required to elevate a 1.6 kilogram book 1 meter. Pause the video to work on the problem. Did you get 19 joule? What work is needed to increase the speed of a 26 kilogram cart by 3.8 meters per second? Pause the video to work on the problem. Did you get 190 joule? A 1,250 kilogram wrecking ball is lifted to a height of 12.7 meters above its resting point. When the wrecking ball is released, it swings toward an abandoned building and makes an indentation 43.7 centimeters in the wall. What is the potential energy of the wrecking ball at a height of 12.7 meters? What is the kinetic energy as it strikes the wall? If the wrecking ball transfers all of its kinetic energy to the wall, how much force does the wrecking ball apply to the wall? Why should a wrecking ball strike a wall at the lowest point of the swing? Pause the video to work on the problem. Did you get 1.56 times 10 to the 5 joules for the amount of potential energy? The conservation of energy says the potential at the top must equal the kinetic energy at the bottom, and so is also equal to 1.56 times 10 to the 5 joules. The force is the work done. From the work energy theorem, the work is equal to the change in kinetic energy, which is 1.56 times 10 to the 5 joules, given a force of 3.57 times 10 to the 5 newtons. When the wrecking ball is at its lowest point, all of its potential energy has been converted to kinetic energy, thus striking the wall with the greatest velocity. Your assignments are to read Chapter 8 in the textbook, to watch the videos on Blackboard. Your homework assignments are due March 9th.